in this last unit, we're going to take the representation from the previous unit, the neural radiance field, and try to build a generative model for it. Try to build a model that is capable of, given just a collection of 2D image of a particular object category, builds a generative 3D model that can be rendered photorealistically into new images. The difference to before is that NERF has always been optimized for a particular scenes given many viewpoints where the camera poses have been known. Now we don't assume any such thing. We just assume that there's a collection of images of objects of a particular category, and we don't even know the camera pose. And we want to build a generative model for this. And this is what we call generative radiance fields, or graph in short. Before we start, let's quickly recap generative adversarial networks. These are slides from the deep learning lecture that you should already be familiar with. The term generative model refers to any model that takes a dataset drawn from a data distribution P data and learns a probability distribution P model to represent that data distribution. In some cases, the model estimates P model explicitly and therefore allows for evaluating the approximate likelihood P model of X of a sample X. But in other cases, the model, in many cases, this is not intractable. So the model is only able to generate samples from P model. And GANs are prominent examples of this family. This family is called family of implicit models. So you can see this is another occurrence of the term implicit, but again in another context, but it fits the spirit of this lecture. So here implicit means that the likelihood is not represented explicitly, but only implicitly. So GANs provide a framework for training models without explicit likelihood. And this is what we have seen in the last deep learning lecture. This is the prototypical diagram of a GAN. There's a latent code sampled from some noise distribution. And so we get that latent code and we input that to some generator network that produces, in the case that we've seen in the deep learning lecture, just a 2D image. And then we have a discriminant network that takes this image and tries to classify if this, what it sees as an input, X hat or X, which comes from the data distribution. So these are the same networks here. If that is a real image, or if this is a real image, or if it's coming from the generator distribution. And we're training this model using this two-player minimax game paradigm with a value function specified as such. And the discriminator try to optimize both the generator and the discriminator. So the generator tries to produce images that are more and more realistic, and the discriminator tries to distinguish them. And if the generator becomes better and better, then the discriminator has a hard time, and ideally, in the end, will be completely uncertain. We'll assign 0.5 probability to all the samples. That's GANs in a nutshell. We have seen in the deep learning lecture that the theoretical analysis shows that this minimax game, as specified here at the bottom, recovers using some very, very strong assumptions, in particular assuming that D star can be reached at each iteration, recovers the data distribution as the model distribution, and also assuming that the model has, of course, enough capacity to represent the data distribution. But in practice, reaching D star, the optimum at each iteration, is too slow, and so we must use iterative numerical optimization. And optimize D in an inner loop to completion is just not possible. So we have typically an alternating optimization where we do 1, 2, 3 steps of optimizing D in the inner loop, and then 1 step of optimizing G using a small enough learning rate. And this way we maintain D near its optimal solution as long as G changes slowly enough, which in gradient descent typically it does, because we can't do very large step sizes anyways. And we have seen this little 1D example. Here we have the data distribution in blue, the model distribution at the initial iteration in orange, and the discriminator here in green. And this is the noise distribution in red. And if we start optimizing, this is iteration 500, iteration 1000, 2000, 2500, we see that the model distribution converges to the data distribution, and the discriminator becomes more and more uncertain and close to, so here's the axis for the discriminator, probability close to 0.5 for all the samples. Now, let's take this idea and apply it to radiance fields. So we want to build a generative model for radiance fields. We want to sample a latent code that captures a 3D point location, a viewing direction, and information about the shape and appearance of the object, as well, which is not shown here, as well as the camera pose. And then for that point, using the radiance field, we can predict the color and the density. And then we can use volumetric rendering to render the scene. And we want to render the scene such that a discriminator applied on that scene, on that images, a 2D discriminator, can distinguish between real images from the data set. This is all trained just with 2D images, and the renderings from the model. This is the idea behind graph generative models for radiant fields, which has appeared at NeurIPS 2020. And we train this from unstructured and unposed. Unposed means we don't know the pose of the cameras, 2D image collections. A particular challenge here is that we can't directly apply a discriminator in 3D because we just have images as observation. So we really need to apply this volumetric rendering, which is slow. And this is one of the contributions that this paper does, is how to make this tractable. So let's now step by step build up this model. We have a radiance field here that we know already that maps a 3D point X and a viewing direction D. And this gamma here just is a positional encoding as for nerve. So we push these both to a positional encoding. And this maps it to a color and a density. And then for that ray, we do this, well, we do this radiance field computation for multiple samples along that ray. So X changes. We have an index I here because we have multiple samples along the ray. The direction is always the same. And so we evaluate this conditional, this radiance field is not yet conditional. This radiance field is nerve for all of these points along the ray to get for all of these points color and density. And then we apply volumetric rendering, which is abbreviated with pi here, but is what we have discussed before, the standard alpha composition in order to render a pixel's color from these endpoints along the ray. This is how nerve works. Now what we add here is two additional latent codes. One is a shape latent code and one is an appearance latent code that are also sampled from some standard distributions, normal distributions, and that are responsible for modeling the condition of, well, the rendered image on the shape and the appearance of the object. Now, because we can't render the entire image, which would be much too way too time consuming, what we do instead is we render just a few pixels. In particular, we take a patch. This is shown here as a 5x5 patch. In practice, we use a 32x32 patch. So we take a 2D image grid, and the location and stride, the size of this image grid, is sampled randomly. So only for those 5x5 or 32x32 pixel locations, we do this process. And that is what we have here with R. So this plate here denotes that we do this R times, where R is, let's say, 5 times 5, 25 times we do this. K is the intrinsics. Xi is the extrinsics that come from the that are sampled also randomly. Here in this case, we assume the intrinsics are known, but you can also sample the intrinsics. And this new parameter here is responsible for placing this sampling grid, this sparse grid on top of the image plane, which determines then where the rays are located that we sample from. So it's very similar to NERF, just that instead of sampling for all pixels in the image that we want to render, we sample just a few of them. Right? And so we get this predicted patch here. And the sampling pattern hue here changes the location and stride arbitrarily, because at any scale and any location we want to produce a realistic patch. Right? But we just produce this patch. But because we have a 2D patch, we can apply a standard convnet now. And this is very fast. So we apply a small convnet that is basically discriminating that predicted patch from a real patch that is sampled from real images using the same pattern generator. Here we also have the new that generates this sparse pattern at a certain location with a certain stride from this random distribution. And we sample a random image from a data set, and we get, therefore, a random patch. So we compare these two with a 2D discriminator. And the 2D discriminator is a simple 4-layer convnet. So this is very simple. Now we've reduced the problem because we don't need to render the entire image, but we just do sparse sampling of the image and compare these very small patches. And this is fast enough and takes little enough memory to be able to be trained in the context of a generative adversarial network objective. You can see blue is the generator of the generative adversarial network, and red is the discriminator. The discriminator is a 2D convnet similar to standard GANs, but the generator is generating a 3D structure that's rendered into an image, or more specifically into this little patch that the discriminator tries to discriminate from real patches. Here's an illustration of the conditional radiance field network architecture. This is this block here. And as I mentioned already in the beginning, we have a shape code CS and an appearance code CA, but how do we make sure that they are not entangled? Why do they represent different things? Well, similar to NERF, the volume density sigma depends solely on the 3D point X here. And not on the view direction D, which is injected later into the network. And it also depends on only the shape code CS, because the appearance code is later injected. We first want to model the shape, and then the appearance is typically something simpler that we can model with a model that has less capacity, so it's injected later. The predicted color C then additionally depends on the view direction and this appearance code, but there's less capacity in this last part of the model, obviously, because we've already done some computation here. So this color head needs to then adapt the color using these conditions. And this allows to model view-dependent appearance, for example, specular materials. That's all. So let's look at some results, and Katja, the PhD student who did this work, did a beautiful video, so I want to show you simply this video.
Hi, I'm Katja from Tübingen University, and I will talk about 3D-aware image synthesis with generative radiance fields. This is joint work with Yi Liao, Michael Niemeyer, and Andreas Geiger. While generic GANs can synthesize high-resolution images, they cannot model 3D properties like viewpoint changes explicitly. But we want this. We want to make generative models 3D aware. But 3D supervision is difficult to obtain for real-world data, so the question is, can we learn a 3D aware generative model using unposed 2D images only? Existing approaches rely on voxel-based representations. They either generate the full 3D object or an abstract, low-dimensional 3D feature that is decoded with a learned projection. While the latter reduces discretization artifacts and memory requirements, the learned projection can impair multi-view consistency. This can be seen particularly well in the 3D reconstruction from the generated images. Inspired by neural radiance fields by Mildenhall et al., we propose generative radiance fields to replace voxel-based with continuous representations. This scales better to high resolution, avoids a learnable projection, and allows generating 3D consistent images from 2D images only. So how do we learn to generate radiance fields? We start by sampling a camera pose randomly on the upper hemisphere. Following a patch pattern, we select a fixed number of camera rays. On each ray, we sample 3D locations to which we concatenate the viewing direction of the ray to create 5D coordinates. We embed the coordinates with a positional encoding and concatenate a shape and an appearance code. Our generator predicts a volume density and a color value from the inputs. Note that changing the shape code will correspond to a change in volume density, while changing the appearance code will modify the predicted color. The radiance field is predicted for every sampled location on the ray. Next, we compute the pixel value using volume rendering. The pixel values from all rays form a patch. Lastly, our discriminator compares the generated patch to a patch sampled from a real image. Let's look at some results. While all methods work reasonably well for small images, at higher resolution, voxel-based approaches either get too memory intensive or fail to disentangle viewpoint and identity. Our method scales well to high resolution and further produces a depth prediction because we learn the full 3D object. The two latent codes allow to manipulate shape and appearance independently. Our method also works reasonably well using unposed natural images. If you like our work, visit our webpage and check out Graph on GitHub. Thanks!
Great. One final work I'd like to mention is Giraffe. Giraffe has just yesterday received the CVPR 2021 Best Paper Award, and it's an extension of Graph to compositional scenes. Instead of modeling just a single scene using a radiance field, we have multiple radiance fields here that are composited together into a representation and which allow for disentangling from just 2D image collections alone scenes into various objects. We don't have time to go into details into this method today, but I encourage you to have a look at the paper, and also there is a nice blog post on our website and a good video from Michael about his work. Let me summarize. We've seen various neural network as continuous shape representations, as continuous material and appearance representations, or motion representations. For example, we have seen occupancy networks, which was one of the first, and came out at the same conference as scene representation networks and deep SDF, which follow a very similar principle. In occupancy networks, given a 3D coordinate, these are all coordinate-based networks. Given a 3D coordinate, we predict the occupancy. In contrast, deep SDF predicts assigned distance. A neural radiance field takes as input the 3D coordinate and the view direction and predicts color and density. In differentiable volumetric rendering, we predict the color and the occupancy from a 3D location. And in Graph, we take the 3D location of the point, the view direction, and a latent shape and appearance code to predict the color and density. But always we have this little pretty naive MLP as a simple predictor for these implicit representations. So let's sum up coordinate-based networks. Coordinate-based networks form an effective output representation for shape, appearance, material, and motion. And they don't require any discretization and are able to model arbitrary topology. They can be learned from images via differentiable rendering, as we've seen. And there's many applications in 3D reconstruction, motion, estimation, view synthesis, but also we have recently done some work in the area of robotics and self-driving where these representations proved to be useful. However, they are implicit. That means certain properties such as geometry must be extracted in a post-processing step, which takes some time. And extension to higher dimensions is not necessarily straightforward due to the course of dimensionality. We've also seen that the fully connected architecture the global conditioning lead to over-smooth results and also the low dimensionality of the input. But there's promising directions such as using local features like in ConfNet or PyFu, which is also related work, as well as better input encodings as proposed in NERF. And also there's a lot of work on new architectures. For example, there's a work called Siren that uses different architecture different from a ReLU MLP to achieve better results. That's all from my side today. Thank you very much for watching.